So, caveat, the discussion on locks that we did beforehand, albeit might be quite straightforward, also is required to understand the monitors in here. So for that reason, I'm asking yet another time, do you have questions regarding to locks or synchronization or anything of the like? Because now we're going to see one topic, which is actually the one also related to the coursework itself. So the thing that we were all aiming for. Yeah. So this is just a recap of whatever we said this morning. Scheduler-based solutions in object-oriented programming offer classes encapsulating the desired synchronization behavior. So what does that mean? It means that basically, if you're using a lock or if you're using a test and set in the way that I was implementing that, and in Java from the book, that gives you somehow the notion of encapsulation, but that encapsulation is just for the concurrency control. As we'll see next week, semaphores also provide little abstraction typo, as they just encapsulate the desired synchronization behavior. Because in there, the only thing that they're doing is just remembering differently from what you'd have with monitors, that you send a signal. In here, you have no recalling of whether you're sending the signal, you're just letting someone inside a critical section or not. So, on the other hand, we want to design a framework encapsulating both data and synchronization mechanisms. Because now, as far as you can tell, all the variables are outside in the wild, and then you're using codes or locks externally, so to have basically so to have encapsulation of what you're doing. But ideally, you want to create a construct which is completely transparent from the notion of concurrency. And then you're adopting one methodology for hiding or encapsulating both variables and concurrency control. So everything is completely opaque to the one invoking the methods. So that is actually what we're going to talk about today, this afternoon, which are monitors. We're going to introduce to something that might be there if you're just having a look at old books. And because actually if you're taking old Java books, you'll have a difference between between monitors in Java and however realistic monitors, monitors look like from the theoretical standpoint, which is you're having a queue and you're having multiple waiting queues for waiting on multiple conditions. That could also be achieved in Java by exploiting the newest constructs, which are going to be discussed in here, that's for sure. So, too fast. So those are going to be different from Hoare's monitors that we're going to see after this prelude. And then in here, as you were seeing today, each object is already associated with a lock. That could also be used to ensure mutual exclusion. So we've seen, you could also, if you are inside a class, you could use this, and that will be basically the object on which you're doing the mutual exclusion. But in addition, you're also inheriting other methods that can also be used to do synchronization techniques. Those are going to be quite simplistic, and they're going to go well only if you have at most one waiting condition. So, how are those waiting queues called? They are called condition variables in Java. And those are the ones providing extra waiting queues, depending on the different occasions that you are considering. But everything is going to be clear once we provide like a description of the Hoare monitor, even because that is going to be more general, so you have a better idea. At the moment, the only thing that you have in a Java description of wait and notify is that the wait method is going to be the one for which you're waiting indefinitely. So it's different from a join. A join actually waits for a thread to terminate. This wait is actually waiting for someone to that is going actually to send me a notification. And that is going to be triggered by a notify method. And the other thing that you have is actually notify all, via which you're not necessarily notifying one of the elements, but you're notifying everyone waiting for the specific condition. So then the idea is, what is then the semantics of wait and notify is provided in here. You know that every object, as we were mentioning, is a lock, is acting like a lock, and has also a wait set of instructions. Then I'm going to add on parentheses a wait, because then for the other waiting condition, the waiting is going to be a wait and not wait. And that is going to be like an important difference, because if you're using like a waiting condition and you're using wait, then you're going to use the old Java monitor assumption for waiting. But if you're using the waiting conditions, the thing that you want is actually the wait. So the difference between this description, these waits, and the other one is just going to be a matter of a. So that's why they are within parentheses, because the same idea will happen. So, and then, as I was mentioning before, wait is acting like a waiting queue. So in there, you have all the threads that are specifically waiting to be waken up by a signal. And so, whatever will happen, otherwise you would have a deadlock for sure. So the additional intuition is that whenever you're doing a wait call, you're also implicitly releasing the lock. So you're allowing another process to go inside. So that's why we are explicitly synchronized for that reason. So you're avoiding basically, now I'm waiting for a condition and then I'm creating a deadlock. No, that is not going to happen by design. And then the thing that you're also going to do, then whenever you are going to wait, then if you have any other process, then it's going to pick an arbitrary thread and then going to see that, for example, was trying to go inside the lock, for example, and that is going to be scheduled. But that is going to be if I'm waiting and no one, so I'm going to wait and no one is actually going to be signaled. With that, then another thread could also go inside the critical section. But the thing that I'm referring to now is actually point number 4 from this item list, which is a call to notify. So the other method, notify, picks an arbitrary thread from the waiting. So in here you see they are not ensuring necessarily the FIFO-ness, so first come, first served. So it's not going to be necessarily a queue. But that might be also enforced in reentrant locks by specifying the true parameter that we were seeing before. So in here it's just an arbitrary element, you see. However, the thread must reacquire the monitor lock before it's able to return from wait. So the thing is, I'm waiting, and then if someone else was notified, okay, I'm notifying someone else, and then as soon as you go back to resume my computation, so I quit the wait, then I will reacquire immediately the lock to the entire critical section. And that is actually stating the obvious, the thing that I stated before. Given that I'm picking one random thread from the waiting queue, then I have no guarantee to have like the be waken up in a specific order. So that's why also reentrant lock are preferred. And then that is going to be similar as per the second set of slides, given that whenever you're waiting for something, also another bad thing could happen, then at this stage I could also have an exception. So in all the time that I'm waiting for something, I could also wait for a signal, not necessarily the notification. And that's why while waiting, I could also have an interrupt exception. So that is also the reason why it's actually better to safeguard all the waiting conditions to check that actually the thread is not going to be interrupted. So you know that potentially whenever you're waking up, it could also be in like an interruption, not necessarily someone notifying you. And that is also the difference. Notify just picking up one single thread, while notify all is going to take all the threads automatically and notify everyone one by one, so not necessarily at the same time. It depends also on the scheduler policy. So even in this regard, then you have everyone being rescheduled, but you don't know even in this scenario in which way you're going to have the threads coming up. In the same way, you don't know a priori which order the schedule will follow before running the program. Buffer using object monitors. Yeah. So then the thing is, now we're going to see basically one use case example on how to achieve one simplistic monitor by just using synchronization using this kind of old technique. And we're going to use a very simplistic use case example where you have one producer and one consumer. In this regard, you have one producer and another consumer that might get the data, and then we're going to discuss if that works from multiple producers or multiple consumers too. And then we'll also need to discuss what would happen if we use notify instead of notify all. But those are the questions that they're trying to answer. And this is actually the code, which is also providing why this kind of old way to do stuff is quite clunky. So in here, I'm using the old Java monitor, so I could have done like used the synchronized method, or I could also use a synchronized block. So in here, I'm using synchronized as a keyword for the method itself, either put or get. And given that I have only two methods inside my class, that is actually guaranteeing somehow mutual exclusion while accessing the variable, because all the variables are kept private. Then I know that in Java, you could also force the virtual machine to access a private variable and change it, but that is actually beyond the control, okay? You could always do this kind of clunky stuff in Java. Even though it's private, you could always access a private variable. If you know that it's declared in there by name. Anyhow, the thing that you could do then, given that you have a synchronized as a keyword, then you have that the object, so the instance of a bounded buffer, is actually going to be the lock for itself. And then the same lock object will have a wait method. So, and this kind of queue, so what is actually the queue doing? The queue is just keeping in memory all the messages that are there, that are received. So you have like a synchronous call, in as much as if you're trying to get something while the queue is empty, then it's going to wait. You might have another method which is full. For example, if you have a bounded buffer for which you have like a maximum amount of elements that could be there. So if the queue is a bounded buffer with a maximum size, then you could also wait indefinitely, so not to provide another message unless someone is consuming at least some tokens, so to deplete the queue, so one extra element could be added. So you see in here, I have two while conditions, and I'm waiting for two different occasions to happen. So then let's start from the easier question. Why it is required to notify all for the condition, and why, or why not, replacing notify all with a single notify would work. The hint is that everyone, be them wait whether the queue is full or the queue is empty, are going to be wait in the same environment of processes waiting for something. So what would happen? Do you have any kind of assurance that the thing that we are notifying at the end is going to notify the right stuff? in as much as the notification at the end of the get is telling that I have depleted one element from the queue, and the notification on the put is actually signaling that I inserted a new element. So basically the notification of one has the aim that whoever is waiting for the queue to be empty, then so it's not to be empty, then you would know that now they are allowed to remove one element without throwing an exception, and whoever wants to put an element under the assumption that the queue is bounded, so that's why you have that n, then is going to be allowed to put one extra element because the queue was depleted. So what if I'm replacing notify all with all? Do I have any kind of guarantee to which process I'm sending the signal? Anyhow, the answer is no, because everyone is waiting within the same queue. So if I'm just notifying some thread, I don't know which thread I'm going to notify, because I cannot select precisely to just wake up one thread waiting for provide an element and so on and so forth. So in this scenario, then you could also know that it works for a single producer and consumer, and we could also work for multiple producers and consumer. It's just that is going to be quite clunky, by the way. So it's going to work, but it's going to be very slow because you are all the time you are waking everyone up, and so it's not going to work as you might expect. Exactly. So that is actually the thing provided on the top. So that's why it's somehow general, also handling multiple producers and consumers, because you have notify all, which is actually ensuring that you're just waking up everyone all the time. But that implies that you have some threads might be waking up and then will have to wait again, which is actually rather inefficient. So the idea would be that I want to have a data structure that is just going to notify the elements that are waiting for retrieving something rather than notifying everyone else. If there are multiple waiting conditions, then we need to differentiate them somehow in different waiting sets. And so in order to do that, then we want to use at its best everything which is available in the concurrent package, which is going to discuss now proper monitors, so the Hoare monitors that we were discussing before. Before we add stuff, do you have questions regarding standard Java monitors? No questions? Okay. So that's why I was saying it was actually quite despicable that when they designed the language, they didn't use straight away Hoare monitors, because they were introduced in 1974, and actually Java was developed in the 90s. So it's like saying going back more than 20 years, like when there was no research on monitors and concurrency. And so nowadays you have a better and updated version of Java that also allows you to do monitors as they were meant to be. So you have a paradigm for concurrency that are allowing data encapsulation, but then is actually the way you are using the locks and the conditions. So that is what in programming is called pragmatics. So it's just how you're using code, and is beyond the correctness of the code itself. So you might have different solutions that have different pragmatic decisions, for which still you might have a correct solution because they're achieving the same result. So in this situation is also suggesting you how to use data encapsulation, still is ensuring mutual exclusion, and differently from the other one, then you have differentiated condition synchronizations, because you could differentiate the queue. So, as you were seeing before and for standard Java monitor, if you're just following the best practices on how to program in Java, you would already know that all the methods should be private. Well, actually, if you're going to work in a company, that might be all the time subverted. Why? Because usually doing a method invocation in Java, given that most of the time you don't have like a compiler that is going to optimize the code, is going to be rather inefficient. So they are preferred to directly accessing the method. But that will do under the assumption that the program is sequential and you know what you're doing. Okay. Anyhow, so the academic way that you're teaching stuff is that the fields should be private, so to avoid concurrent modification or direct access to the data. And that is also to preserve not only privacy of the method and ensuring that no one is messing up with the state of the current object, but also in this occasion to preserve the atomicity, so that someone is not disrupting the changes that another method is providing, another thread is providing by invoking a method. Yeah. Then you're also having mutual exclusion, because you have methods that are not synchronized by using the keyword, but they're synchronized by using the reentrant lock, for example. And then you might have private methods that might be not synchronized for the simplest reason that once you are locking a method, which is going to be publicly invoked, then inside of that you'd have just the invocation of a private method. And if you're guaranteeing that, then that should be easy. And so in here, the intuition is that all the processes are going to be halted and waiting for their run, because you also have a guarantee of mutual exclusion. Then instead of providing that in here, that you could also read on your own, I could directly show you the implementation. No, let's postpone that. It's going to be better. You have too much information. So, how you're achieving mutual exclusion. So strictly speaking, you're ensuring that by using reentrant locks or locks. When a thread invokes an operation on a monitor, it has to wait until it can gain exclusive access to the monitor. How that could be implemented by, strictly speaking, by just ensuring that all the methods are safeguarded by lock and unlock operation. So that is just some naming. You're just saying that the thread which is currently running a method of the monitor is called active. And that is actually the second step on top. The monitor implementation must guarantee that only one thread can be active inside the monitor at a time. How you're ensuring that? By using locks all over for each public method. And this can be achieved using an implicit lock variable, the thing that was already said. Each operation must acquire the lock before it is allowed to access the data structure inside the monitor, so not outside. So you shall not create a lock outside for accessing the monitor. You're using object encapsulation, so the lock is inside the monitor, and the lock-unlock methods are called inside. Then you also have examples in the slides and also on the code being provided. So you have also some references on how to do this kind of stuff. With assumption that, as always, as we were discussing this morning, whenever the execution of the method is finished, then you need to release the lock, or otherwise something bad will happen. Then we have like the major game changer, which is actually condition synchronization. So the threads running in the monitor might be suspended, as we were mentioning before, for wait, while waiting for the satisfaction of a given condition, and that is actually very different. So you're differentiating the reason why someone is waiting. So as a consequence, such a thread should temporarily quit the mutual exclusion, as in the previous example, otherwise I would lock everyone inside. Still, threads shall be allowed to re-enter the monitor, and so to regain, for sure, the lock. So that's why also those locks are called re-entrant, because you could go back and forth from the lock if you have a wait. Then I'm just providing what re-entrant lock are. So re-entrant lock has the same behavior as we're discussing this morning, of a lock, and has the same semantics also to the Java object monitor lock. So, for example, with this, for which we're just providing mutual exclusion. And the rendered lock, as always, is owned by the single thread which is running a race condition within it. So all the time, then the threads will call lock method to acquire the lock and unlock to unlock it. And just restating the obvious all and again. What is actually the main game changer, if you are just using an object, then you don't have a possibility of invoking a method which is called new condition, and that is going to generate for you a new condition associated precisely to the lock. So a common error is actually to create a new condition, and the condition that you're providing is going to be used within a different lock. Then from the code perspective, maybe you are instantiating a new lock somewhere in the code, which is not the one that had generated the condition beforehand, and then Java provides you the error, which is quite common in the courseworks, in their initial stages still, which is, okay, I have the condition, but that is associated to, so the condition was run, but was associated to a different monitor, and you're trying to run the wait or signal something within a different kind of lock. And that is actually the usual error and the usual common mistake. So it's going to be better that monitor shall have only one lock extensively, and then you have multiple waiting conditions. That is actually the way to structure this. As a consequence, you cannot reuse the same methods that you were using for wait, notify, and notify all, because those were not overridden. And given that you have ambiguous semantics in Java, but you could also use an object for locking and unlocking, they were not extending the method also for waiting, notify, notify all for the new waiting conditions, for which you have specific other methods, await for waiting for something, signal for signaling that the condition happened to the other one waiting, and then you have signal all. So you have exactly the same semantics that was discussed before, it's just the naming that was different. And in here, I'm just providing an example of this code. So let me discuss that with you. So in here, I'm trying to create something called a barrier, so a barrier in here. And this is going to be something quite simplistic. So you have a monitor, and the monitor for you is going to be mainly within that variable, lock monitor, for which you only have, in this scenario, only one condition variable, but that is just for start. Then we will complicate that later on. And then you have two things, a counting and a waiting. So what is actually the purpose? The purpose of this code on the right is to have basically some threads starting to execute, and then you want to wait for 10 threads at a time, and then after you wait for 10 threads, then all the other threads could resume their computation. So hello world as a method is just acting as a barrier for which they're waiting for at least 10 threads, and then they're letting all the other 10 go. So for this, then, to this monitor or lock, you're associating a single variable in this scenario, and you have some counters that are initialized to 0. So in here, by default, Java is initializing integers to 0, but that is still enforcing the obvious. So how will the synchronized method behave? So given that I have a new element, I'm just incrementing the counter. I'm allowed to do that because I am within a lock. I didn't add, just because this slide was too short, the try, finally, unlock, but that will do. So, and then in here, the thing that you're doing is incrementing the counter. So you have a new thread, which is actually using the method. Then you're checking whether the number of counter is less than 10. In this situation, you're incrementing the number of the elements that are waiting, and you are setting up the await, not the wait, because you are waiting on a condition within the lock. So then I'm decrementing the counter for waiting. Then let's see if you know the idea why I'm doing that. And then if the number of waiting is still greater than 0, I'm saying, okay, I have still someone that is waiting for the condition, and given that I was waken because I'm after this counter, so it means that no matter how I passed the test, and so either I was waken up or the counter was greater than 10, and so I know that someone is waiting for be signaled. So in here, yeah. So in here, then I know if I'm at this region that I could potentially signal someone if the value is greater than 0. And then definitely I know that now have been rescheduled. And the very important part is that the order of execution will be reflected by reentrant lock. So if I pass no true argument to the reentrant lock, by default is like having false. So the waking up order is not a queue necessarily. If I specify true, then I'm waking up the threads in the same order they were starting to wait. So in the same order they acquired the critical section within the method itself. So you see, you might also have like a meta lock by using a barrier. So you could also use another critical section to implement another larger critical section. And that is going to be the idea that we're going to analyze by the end of today. So going back to the question, so do you know why I'm incrementing the number of waiting in here and then decrementing that afterwards? Do you know what is the rationale for doing that? I on purpose left that out from the explanation. So that is mainly because I don't have the access of actually the waiting queue. Then if you're using like reflection and you're trying to access to the internals of the variable, you could also access implicitly to the name of the threads that are waiting. But if we are not forcing the Java library, then we cannot know how many threads are waiting. So the rationale is that I have a counter to remember if it makes sense to send a signal to someone, and that is actually what I'm doing. And therefore, as a consequence, I need also to remember to decrement the variable. Otherwise, I might have no one waiting and still try to send a signal, which might be like counterproductive. So you might send a signal to no avail. So that will just add safety guarantee. So you actually know how many of the threads are waiting. And definitely, if someone is sending a signal to you, and then you're waiting at this point, then you continue the execution. And definitely, you are going to decrement the value of waiting by 1. Before I provide like an overview on how and recap, okay, so let's do that instead. This is actually the graphical depiction of what a monitor in a general way is actually going to look like, okay? So it's like having a room, and that I think it was from Wikipedia, on which you are entering the monitor by using the critical section between the lock and unlock. And in there, you might have like an entrance queue, for example. If the reentrant lock is fair with a true parameter. If that is fair, then one at a time, as requested by the monitor specification, and given that locks by design are providing module exclusion, you'd have one thread only executing any kind of critical section across the class, therefore achieving that only one thread at a time is accessing the monitor itself. Then the thing that you have is either you're signaling something, and that is actually the other addition that was not specified before. And so what happens to the threads that are signaling, also the threads that are signaling are being paused. So the thing that would happen is that if a thread is signaling another that they could continue, they are put in another waiting queue. And within this waiting queue, they're waiting basically for their time as decided by the lock, so to re-go back inside and acquire the critical section. In the time being, then, if I'm signaling something, then I could signal precisely either the wait for the condition A or the wait for the condition B. So the signal, differently from traditional Java monitors, are going just to signal one specific queue of waiting queue, so each different new condition that you have on the left, and you'd have the possibility of signaling one process at a time. Even in this scenario, the FIFO-ness will depend on the reentrant lock itself. So what is actually the difference between using reentrant locks with new conditions or condition variables and using Java monitors? Basically, you have the same mechanism, but you are forced on having only one wait condition. So you could signal and you have the same behavior once you're signaling, you're pausing itself and then allowing another thread to go inside and reacquire the mutual exclusion. Otherwise, basically, you are continuing your computation and then eventually you will leave the critical section. So do you have questions regarding this explanation or on the difference between Java monitors and Hoare monitors, like these ones, that are also usable through condition variables and reentrant locks? No question. Either everything is exceptionally clear or it's Friday afternoon, one of the two. So, condition synchronization, then what are they doing? So let's see that in more detail. I'm just restating the obvious all the time, but just to clarify. Sometimes a thread that is executing inside a monitor needs to wait until some condition is true. As we were saying before, for the bounded buffer, so for the first monitor, you might have two conditions, one for which you're waiting the queue to not be full, and the other one that you're waiting the queue not to be empty. So the condition will become true as a result of some other thread actually invoking you. Otherwise, you have a deadlock in the design of your concurrent algorithm. So in order to do this kind of two-way communication, then you need to achieve condition synchronization, which is the third block. And so by using condition variable, you could precisely target what to wait for, which is the fourth block. A thread can wait for a particular condition to become true, and another thread can signal that the condition is now true. Okay, also restating the first one, just reshuffling that around. And while a thread is waiting, it releases the lock on the monitor, allowing other threads to enter the monitors. Otherwise, you'd have a deadlock. So you also have that by design. So in here, I'm just providing all the possible ways you could achieve, what are they called? Like the bounded buffer monitor. So the example from the very beginning. One is the lazy version, what is I have only one variable. I don't have all the variable to access. I just have a linked blocking queue. As a consequence, I couldn't care less whether I'm using a monitor or not. I'm just having one variable. That might be also a fair decision to do if your program is just sending data across and you have only one waiting queue. Then in here, the linked blocking queue, anyhow, is the monitor that you're using. It's just that you haven't implemented them from scratch and you're using that library, which is already a monitor. So if you want to know how they're handling that with a data structure, it's going to be somehow quite complicated. So even in the traditional Java, you have additional checks that are checking whether the data structure is changed concurrently, and if not, they're throwing an exception. So it might be quite redundant looking at actual Java library implementation, but anyhow, it might be interesting to see. So in there, I need also to declare what should be like the boundedness, so the maximum amount of elements. In this occasion is actually 10 elements. I could start 2 threads. As always, all this code is actually provided in the Maven package. So you might have 2 threads, one for the consumer and the other one for the producer. And then I want just to, for example, put some elements. So in here is going to be more simplistic. So you're not even providing a bounded buffer. I'm just doing 10 iterations and that's it, just to clarify. So for 10 iterations, I'm trying to take an element which is trying to get an element while waiting, because again, given that this monitor is also synchronized, you could also have different methods. One which is trying to get one element, but if it is empty, is not going to wait. Another one which is actually waiting, which is the stake, if nothing is there, and so on and so forth. And then you have the add method, which is guaranteed just to add to the last part of a queue. So it's just a push method, and the take is acting like a pop method for the queue. And then after that, you could just start and join the threads, and they are going to behave similarly. So this is actually from the external reference what a monitor should look like, which should be like completely opaque to the actual concurrency handling which is happening under the hood. But then I think that before even talking about that, it's going to be easier if we're going to talk about the bounded buffer first, before introducing read and write lock. And we're going to discuss those more extensively after the break. So this is actually the other example about bounded buffers, which is implementing the thing that we were seeing at the very beginning with just Java monitors, but with reentrant blocks. Thus also should help in asking the question, what is the difference between using a linked blocking queue or using Java monitors or using Hoare monitors with reentrant blocks and waiting conditions? So even in here, what is actually the difference? Given that I'm planning to use critical sections, then you could also use a queue which is not necessarily synchronized. And you see differently from the initial example, you have 2 waiting conditions, one which says that it's okay to read and the other one which says that it's okay to write. So you have 2 conditions. Then you have a mutex. I just provided that naming, but even confusingly is not a mutual exclusion. So it's just is achieving mutual exclusion, and some literature also refers to that as a mutex, but really it's a lock. So I just wanted to provide another name. So that is a lock. And then I get what is actually the maximum size, and similarly to the initial code, I know how many threads are waiting. So I know which is actually the maximum size that the queue should have. I'm creating like the field, the mutex, and I'm creating 2 different conditions, and I'm setting the initial number of elements that are waiting to 0. So that is actually answers the question, then if I have a lock, where should I declare it? As such. So that is actually going back to the answer that I gave to your colleague this morning. Okay, then this is actually the implementation for the bounded buffer, for the put, and for the get, we're using reentrant locks. So you'd see in here the code is actually becoming longer than the other one, but somehow is clearer what is actually going to happen. So in here, as always, you're always locking between for each method. So at the very beginning, I define which is actually the critical section, is whenever I'm doing operations with the conditions and I'm doing operations over the message queue. With the get, as I was talking about this morning, you have like the local variable, which is just val, outside of the critical section. Why? Because you'd have a different val for each stack, for each thread. And then you're just returning that local value to the thread that was calling the get method. So that's why that is out of the critical section. Similarly, on top, then you know that you are just waiting for one condition, which is getting whether the queue is full, which is actually reflected by the size of the number of messages being on hold is actually greater or equal to the maximum size. You could also say equal, but that is just adding some safety guarantees in addition. And then in here, precisely, I'm saying that I'm waiting for the writing condition. So it's clear what the code is doing. I'm waiting just to write. And it's also going to be clear that the only way I'm going to get the notification, so it's not because I'm putting one element that I could notify another thread which is waiting to put. So given that I put something, that is actually somehow straightforward, but I could also be not efficient, and that is actually what is happening. I'm not checking how many threads are waiting, but if I could also do that. So if there are other threads that are waiting to read, potentially that is also the thing that I could do. I could increment the number of threads waiting to read, and I have another variable checking how many threads are waiting to write, and send the signal only whether the number is greater than 0, but that is not provided in here. Anyhow, I'm just signaling that given that I put one element, then you have something to read, and so whoever was trying to wait, then that might be waking up. The other thing that I want to restate within this code is that if you're sending a signal, which is the signal, and then no one is waiting, then if the code is actually badly designed, then you are going to wait, but no one is going to wake you up, because you need to guarantee that whenever the waiting condition is applied, then you need to wait, because you need to wait for completion. So if someone was already sending the signal, you need to remember, if you need, that the signal was sent, and so you do not need to wait anymore. So in these occasions, either your code is badly designed, or you need somehow to remember this. It's similar to the interrupt. You have like a join or a sleep, and then you're sending an interrupt, and then the thread is actually waking up for the interrupt, and then if you are not signaling the thread on the time where actually is waiting, then the signal is lost. So that is also important to mention. And then you have the dual with a get. So given that, so I cannot get an element, otherwise the remove will throw an exception. If the queue is empty, so in those occasions I'm just waiting. Otherwise, I'm removing the first element, and then to whoever who wants to write, I'm going to signal, okay, now you could have a chance to add something because I removed one element, so there should be sufficient space for you to write. And in here, I'm using a while condition just for braces and belts, but if you want, you could also have a if condition in there, and they should be working fine. Yeah, and then we're going to discuss after the break about readers and writers and the implementation for strict two-phase locking using monitors and reentrant locks. But before the break, do you have questions to whatever was explained today or now? Then if not, then the last part is also going to be related to the thing that you need to extend for the coursework. So I'm giving you even 15 minutes this time, so you have more time for taking a break, and recollect your ideas. Okay, let's resume. Questions? No questions. Okay. So, readers and writers problem. What is actually the assumption? I'm actually coming from the database literature, so that's why I'm always providing extensive references to databases anyhow. So a database is shared among different number of threads, but you could also think about any kind of other program that you have in your mind. It could also be like a server or what have you, whatever is actually providing distributed resources and in a distributed way, a resource in a distributed way. Then there exists two different types of threads in this scenario. Some readers that are performing read-only queries and writers that are providing bulk insertions, updates, incremental updates. So basically, those are database operations, but the only thing that matters is that you have two processes, one doing read operations and the other one doing write operations. So if you have like the bounded queue as before, you have like getting something or writing something are both write operations because you are updating one variable. If you'd had another method which is size, then that might have been like a read method. So in the previous example, all the methods were like write methods. In here, we want to control the readers and the writers for each possible kind of resource. So basically, we're trying to provide the underneath implementation of the strict-to-phase locking locks. And also the code is provided on the slides, for sure. So even in this scenario, a database or any kind of operative system or what have you should act as a monitor for a specific table, as we were discussing, or a monitor for a specific file. So we want to guarantee that something bad doesn't happen. If a writer accessing a database for updates, it should be the only process in the monitor. For example, I want to update like the date of birth, and I'm accessing from two devices, then I cannot do like the same update contemporarily, otherwise there might be a mess with the final date. If no writer is performing operations, all the readers can concurrently access the database and reading, so because you have no guarantees. So under the assumption that platform is not going to log you whenever you're going to use that, but suppose that you're using like a social network platform, you're going inside and the only thing that you're doing is actually scroll the threads or the posts from the person that you're following or the web pages or what have you, and then you're just doing a read operation. You're not doing any kind of updates because you're not posting a message or anything. So the idea is the locks that we've seen before are just locks or unlocks, and they're just guaranteeing one thread at a time within the critical section. Then, how do we enable the possibility of having multiple threads within a critical section, like in strict-to-phase locking, when you have shared locks? Then the idea is that you're restricting this kind of mutual exclusion to just the lock or unlock invocation, which is the only part now which is guarded by mutual exclusion. So that is actually what is happening. So in here, I provided something like cheeky, which is try to implement read and write locks using semaphores. It might go like a nightmare, but that is actually going to be like an advanced exercise. And we're going to see semaphores next week. And then you'll see why it's a nightmare. Actually, that boils down to how do I implement a monitor using semaphores, more or less. And then the thing is that I'm not asking you to do this because actually I was asked to do that as a bachelor degree student back in Bologna. And the thing is that you need to create another queue of waiting processes, and then you're creating a new semaphore, you're pushing the semaphore on which you're waiting inside the queue, and then when you're popping something in order to remember which process from the queue to wake up, you are invoking like a probieren or another kind of waking up to the other message, and it's going to be more complicated. If you know, and if you want to dip in the subject, and if you want to deep dive into a theory, then you have like a paper uploaded in here on the canvas, which is actually showing, which is actually the procedure to implement basically any kind of monitor just using semaphores, but it's going to be very advanced. I'm not going to ask that to the exam. We don't have time. So that is actually just the life cycle of the reader and the writer, similarly to what I was showing before. So in here, we might have like for synchronization processes, purposes on the monitor, we might have like one reentrant, read and write lock. That is how you would do this without re-implementing everything from scratch. You have a shared lock, and you have an exclusive lock, which are the read lock and the write lock respectively in Java. And then if you have just one process doing read operations, then they're all the time bounding something with a shared lock. So you are given that the good faith of a process by directly just doing a read operation. And whenever you're doing a writing, then the thing that you're having, you're just guaranteeing that the process will only do write access. So you are a priori assuming what the process will do, because you could analyze the query that the thread sent you, and so you know what the thread is trying to do. So that is actually what we want to have. So we want to use our implementation similarly to what we were discussing for the strict two-phase locking principle. Then the idea is, how do I ensure that in this read access is going to be guaranteed to multiple threads? So the idea is, this lock or unlock are going to be over critical sections on which only one thread at a time is going to be accessed, thus also guaranteeing potentially, depending on the conditions, multiple concurrent access on the read part in there. So those are actually the preliminary conditions at the boundary that might be refined later on. So that's why, as I was talking before, and for refining just the bounded buffer example, you might have two counters, one for counting the number of the readers and the other one for counting the number of the writers. Then you need to guarantee, which is if you are going back to the safety condition, so that is not a liveness condition, it's a safety condition, but all the time within your program, this condition should always hold. So either you have the number of readers if it is actually greater than 0, and inside the monitor you have no writer running at all, or you have at most one writer and therefore no reader shall be allowed to access that. And the idea is that when do we know that a writer is allowed to go in? Basically, the intuition is that whenever all the readers are left, you're going to give possibility to a writer to do a write operation. And in here, you might already see that there might be a possible source of starvation in here for the writers. If you have multiple readers that are trying to acquire the resource, and they are always very fast, you might have like a starvation condition. So first we're going to show a simplistic implementation on which we are relaxing that to have starvation on the writers, and then we're going to refine that in order to avoid starvation. So we want to preserve the same kind of life cycle for the reader and the writer, but now we want to implement a class instead. So we want to count in here, so the code is going to be dual. If either you're counting how many are waiting, or you're counting how many of those are available. So in here, we're counting how many of those are inside the monitor instead. And then similarly, I'm declaring one global variable, which is the monitor, which is our enter and write and lock. Providing true allows me to ensure like FIFO-ness. And then I create two conditions, whether it is okay to read or whether it is okay to write. And then the initialization is made explicit to 0. Even that could have been avoided. So what is actually the rationale of this straightforward implementation? You have a lock and an unlock down below. And then the thing that you're trying to do when placing the shared lock is that at the very beginning, you're trying to check whether you have at least something which is trying to write. And then if you have at least one writer, then you are forced to wait. So we are calling wait. Otherwise, you always know for prior assumptions that if I'm waking up or if I do not do the while, it means that I could access and continue my computation. So at this stage, given that I'm still in the critical section and I'm changing a global variable, I'm incrementing the counter. So you see now, that was actually the question, why I'm not using atomic integer for the number of the writers and not an atomic integer for the number of the readers, seldomly. Because I have an interconnection of conditions, I'm checking for a value, then waiting for a condition, and only if that condition happens, then I'm allowed to increment. Otherwise, I have like an hell's-a-popping of things in here, which doesn't make any sense. So the thing that is actually better to do is actually to lock everything, and then whenever you have variables that have mutual interdependencies, and then when you're sure, then you could start doing like read. And the other thing that you could also do is to signal another thread, which is, okay, good to read. So I'm in here, I'm not tracking how many of those are waiting, but I could say simplistically enough that if I'm waking up and I'm allowed to read, anyone, which is also waiting for read, could also be waken up to read. So I could wake someone up from their await. And I'm doing that one at a time, so not to be wasteful. And so I know at this stage, I am inside the critical section. I know that I could wake at most one other. And then the shared unlock is going to be similar, and the dual. So before leaving my shared lock, I need to say, okay, I'm leaving completely the critical section. So I'm decreasing the number of readers. And then I'm saying that if the number of readers is equal to 0, then only at that occasion it's okay to signal a writer to actually start writing. And that is actually what we're going to address now. So with exclusive lock is going to work as follows. So in here, we're always going to wait as a writer if I have at least one writer or at least one reader, anyhow. So it should be like an OR. Sorry about that. Should be an OR. So if I have that while this is actually greater than 0, or the number of readers is actually greater than 0, then I'm trying to do OK to write, and then I'm awaiting. Why? Because I shall be waiting when both the number of writers is greater than 0 and the number of readers is greater than 0 somehow. In both occasions, then I need to wait. So it shall never happen that you have one writer and one reader. So that should be like in an OR condition. Sorry about the typo. And then in that occasion, then I'm waiting. Then I can now proceed to write, and then I'm incrementing the number of writes by ++. Similarly, because now I know that I'm allowed to write. And in here, I could also do similarly. So I'm decreasing the number of writers, and then given that there is no other writer, because by assumption I am the only one writing, then the thing that I'm doing is to say a reader, okay, now you could also read. And only if basically that is good because, how do I say, you still have a waiting queue and you have while true loops. So that's why it's also good. If you're also checking that the number of writers is actually, or the number of readers is equal to 0, actually currently running, then the other thing that you could do is to say potentially, okay, now you're also allowed to write. Then by signaling that, you could also say to another process attending to write that they could also start to write itself. This is actually restating whatever I was mentioning this morning on the notification, so on the signaling. so that you need to remember, I will not restate that enough, that actually you need to remember if you're signaling something and no one is waiting, then you need to double check. But in here, the idea is whenever you're sending the notification, it also needs to be when you know that the state of the resource has changed to allow someone else, which is waiting for the condition, so it's blocked, to continue. So if you have something which is actually a writer, you can only continue where there are no other readers or writers. So that's the only reason why I'm decreasing my variable before signaling. Given that after the signal I will pause my own execution, then I need to do all the changes before leaving the critical section. That is also important. So I'm referring to this signaling in here. So if the signal is going to be related to the decrease, then, and given that after the signal I will be paused in the signal queue, then it's actually important that I reset the state of a value before leaving my critical section. Otherwise, you have like an inconsistency on the states that you're having. Sorry. And so you know that everything is going, the only part where I'm resetting something is actually at the unlock, basically. While you also have another condition when someone is waking up is while you're trying to acquire the lock for reading. That is also another part where basically you are saying, okay, you can also continue. So, and that is actually related to the fairness assumption, which is not met, which is what happens, so the starvation, as I was mentioning before. What happens is there is always at least one other reader accessing the resource. Then you have that writers will be blocked indefinitely, with the new readers always overtaking the writers. So you might, for example, implement one of these policies, either do not let a new reader start if a writer is already waiting, and that requires, for example, to have another variables to check the number of waiting writers. Or, for example, do not let a new writer start if a reader is waiting, and then, as a consequence of these, treat readers and writers fairly. So in a way that you know that they're going to share the resources. So in here, you're not actually, so in here you are increasing the priority by changing the code rather than increasing the thread priority itself in Java. So you are just changing the logical conditions so to avoid the starvation problem. So you see now you have an additional variable, which is WW, which is also counting over the number of writers themselves that are trying to write the specific resource. So that is actually the thing that it was postulated before. In order to do that, you need to check how many waiting writers are there. And so then as a consequence, you want to delay the readers if there is already a write operation or there are other waiting writers. And so how are you going to do that? Basically by adding like a disjunction in the code for like the shared lock. So you are going to increase somehow, logically, the priority of the writers by checking not only if the current reader is trying to do a new write, but also by checking whether you have at least one other writer in the queue which is waiting to write. So in this occasion, I'm always allowing the writers to deplete their execution, and that does not create a starvation for the readers, because you know that basically the writer eventually will leave the queue and basically, yes. And so that should decrease the starvation then for the writers by doing that. And similarly, even in here, for the exclusive lock, then where do I provide like the increment or a decrement for the number of the writers? That is going to be actually before and after the waiting condition. And that is actually similar, extremely similar to what was explained before for the barrier implementation. So for that barrier, if I'm waiting and then I want to remember that, I need to increment my variable before, and then after the wait, I might be waking up, and then I'm actually decreasing the number of the writers. So why actually this implementation will not create starvation for the readers? Because basically you always have an OK to read dot signal invocation at exclusive unlock. So this will be the way basically to guarantee that the execution doesn't have a starvation for the readers. Otherwise, a plausible objection could be, okay, now you solve the starvation for the readers, but still you have starvation for the writers. No, given that you are signaling to the readers in there, then that should not be effective, because you still give the opportunity somehow to someone to continue reading, and you are just waiting for all the writers that are waiting to be depleted, to be handled. And so if you reach a situation that there is no writer, but because no writer is waiting, but there are no writers starting to access the critical section, then you are allowing basically one reader to access it. And that should not cause any kind of starvation. Then, this is pretty much it, the end for today. The thing that we could do is actually resume the lecture on Decker and Dijkstra, algorithm, and Peterson now in the remaining time, with the rationale that that also gives you another way to implement a critical section by not exploiting necessarily locks. So you see that from another perspective, and so on Monday we're just going to finish semaphores entirely. But before we're doing that, do you have any questions regarding monitors or anything that was taught today? Yes? The Peterson algorithm is the thing that was left out from this morning. So the last part of the slides. Does that answer the question? Sorry? I explained that before. Do you have a question about that?
No, nothing.
Okay. Okay, so he's asking about this last sentence, which is, given writers' priority makes sense if writes are infrequent and readers require the most up-to-date information. So it means so it also makes, how do I say? It explains also why this might be required from a practical perspective. The thing that means is that if the writer is starving, then all the readers will always read all the information. And so, given that you are arbitrating the access to the resource, and then you have a starvation for the writers, then potentially no one is going to be able to write data. Okay? To avoid this and to allow a writer to write and to avoid starvation, then it makes sense to give more priority to the readers. In this code, we're giving priorities to the readers not by increasing the Java thread priority, but by checking how many other writers are waiting, and that is the addition making writers with a higher priority to the readers. Why? Because in this example, I'm not only waiting to read if there is one writer in the critical section, I'm also waiting if there is some writer waiting to go inside. So, first condition NW is just I have a writer within the critical section doing a write operation. But I'm giving them more priority because I'm not only checking that, I'm also checking if there is another writer waiting to write and go inside. So now I'm giving more priority because I'm also considering a stronger condition than the condition that I have for the readers. For the readers, they are just accessing the data, and I'm not checking how many readers are waiting to read. So I'm checking more conditions over the writers to make the readers wait rather than I'm doing the vice versa. I don't know whether that explains it. Anyway, let me try to rephrase. So, why doing so is relevant? Why having a starvation for the writers is bad? Having a starvation for the writer is bad because in the worst case scenario, you are avoiding having the latest information. So, then you need to allow a writer to write so that a reader could read information which is new. Otherwise, all the readers will always read old information. To avoid that, you need to somehow increase the priority of the writers, but not by using Java thread priorities, by adding more conditions to a writing condition. So it's like saying, I know that the writer is underprivileged, I'm going to provide more privileges, and those are provided by adding one extra condition on the favor of the writer itself. So the thing that I'm doing is not only checking how many writers are there, because if I have one writer, then I shall not be able to read myself, but even though I have someone waiting to write, then I shall be waiting. So I'm waiting in excess somehow. So I'm extra waiting. I'm waiting even someone is not within the critical section, but is at the moment, but I know that someone is waiting to write. And so that is achieved by also incrementing after I know that I need to wait to write. So by doing so, if you have 3 threads that are trying to write, and then let's suppose that you have all 5 threads reading, and all the 5 threads reading are leaving out, and then one reader is allowing a thread to continue to write, then is going to wake from here, is going to decrement the counter and access the critical section. Still, this access will not allow another writer to write. Anyhow, I'm not giving a starvation for the readers because I'm still trying to signal a reader, and given that I'm trying to signal a reader, the other one will check, okay, now I decremented the number of writers, so that condition on the left is false, but actually the number of writers is waiting, is actually greater than 0, then I'm waiting again to have all the writers depleted, and then you see I'm not giving, so I'm adding extra priority because I'm not waiting on a condition which is just a correctness assumption, but I'm doing something extra, and that something extra prioritizes the writers. So that is another way to put that. Anyhow, any question, follow-up question to anything that I answered before? Yes. think that TCP has a priority mechanism? Could you restate that, please?
There's a, in TCP packets, there's this flag called URT, urgent health, which is to be used to signify that this packet's data is a higher priority than
Well, that is just on networking. I think that is more related to quality of service. So I think, but I might be mistaken, okay? So please double check. That is actually the thing that I could say at the moment. This kind of high priority is whenever you're sending something on the network, so to achieve quality of service. So you're setting one packet as a higher priority, because if you're going to receive the packet on your machine, anyhow, so the TCP is guaranteeing the order of provision of the packets. So whenever you have, like, for example, 1 gigabyte that are sending through TCP, you are chunking up in different datagrams so that they have basically the size of a IP datagram, because that size is bounded, while on the higher level, logically, you have a perception of having different packets. So no, you have the perception of having only one message, but underneath the thing that you're doing is chunking up into differently sized IP packets. So the TCP protocol, what it actually is doing is taking, so given that those might arrive at different orders or different times, then the sender is also providing a progressive ID so that the receiver knows how to reorder the packets. So I might receive packet 5, packet 1, packet 3, packet 2, and packet 4 in that order, for example, and then I need to reorder that before I send this information. And maybe I might do a buffered read on which I'm only reading, for example, 1024 bits at a time, for which, for example, or bytes at a time, yeah, it's better, 124 bytes at a time, for which then, if I already achieved the size of a datagram to reach 1024 bytes, then I'm providing that, like, the outcome of a read. So, in this regard, the priority of the packets itself is given completely by the protocol. So independently from the order the packets arrive, you're always ensuring by using an incremental ID that they're using at the right time. So having that will be increasing the priority of the package to be delivered. So you're adding that time step because the receiver itself, you will receive all the connections on all the packets. So once the packet it goes to the receiver, you have all the packets. So you don't have like a priority list. You have basically all the connections that are going to be handled by your operative system. And those are going to be there. Then to some extent, you might also think that I have that priority marker, then also at the operative system level, I try to prefer that, but anyhow, so independently from which is the purpose of the ID, that is just having another kind of data structure, which is called priority queue, on which you might have values telling which is a priority of the package. So if you're sorting all the data that you have, you know that some packets are more prioritarial of the others. So you're not putting something inside necessarily by FIFO-ness, but you're having first an order that you are enforcing, and second, you're using basically the timestamp for ordering the messages from the same sender. So that might be used also for handling this kind of packets, but that is just a scheduling order. So actually, the question could be, what is the connection between concurrency operations and readers and writing operations? And then for that, let me find a picture first. So, wait a second. So, systems. and finding the image. At the very end. The philosophy. Message passing, here it is. Send, receive, asynchronous. Send, receive. Message passing, send, receive. Yeah, the greetings, send cues. So, message so that image didn't help at all. So, to some extent, the reason why you're using concurrency in distributed computation could be either for handling multiple connections contemporarily. So you have a server and you need to handle requests. Then you could also use a thread pool, but that is actually independent from the priority. But for example, you might receive a message or something, receiving a request with higher priority, and then it's up to the server how to reply, whether you want to prioritize the reply to the message coming from a higher priority. The other thing that you could also think about is that you could mimic a distributed computation with a producer and consumer. So in here, the other thing that you have is basically you have just a producer and a consumer. You could think those as the client of the server. And the queue that you have in between is actually the message queue to the other end of the receiver. So basically, the answer is the only connection that you have between those is either on handling multiple requests, or definitely the thing that you could do is to implement a synchronous or asynchronous message passing through locks and monitors. So if you want, basically you could implement a waiting queue. In a similar way, you could say, like, if I receive no message, but I'm waiting for the message, otherwise once I receive something, I'm immediately returning. Then you also have the possibility of polling. The thing that you're doing with the polling is basically waiting if I have some file descriptors ready. For example, if you have no file descriptor ready, then you're just waiting. Otherwise, you're handling the request. And that is actually the thing that you could do to some extent. So you could simulate through multi-threading message passing. But precisely the part of priority is just the way you're ordering the messages to some extent. I don't know whether that answers the questions, by the way. Any other question? Yeah. So we're going to cover semaphores next week. The difference between a reentrant lock and a semaphore is going to be that a semaphore is also remembering how many signals you're sending. So you have two operations. So it's I just record that from the Dutch name. I don't remember actually the way it's called in Java, fairly speaking. But you have P and V, which is proberen and verhogen. So proberen is actually the wait for the condition of a semaphore, and verhogen is actually the thing that you're saying, okay, I'm adding one count. So basically, as you're going to see from the slides, you could always implement a semaphore using a reentrant lock. And how do you do that? You are just adding one counter, and you're counting how many elements are there. If you're doing a P, then if the value of the counter is greater than 0, you're decrementing the counter and then you're continuing. Otherwise, if the value of the counter is 0, you are waiting, basically. And then you have a waiting condition. So that is actually one response. Then the other question will be to answer your question satisfactorily. Then can you use semaphores to implement monitors? That is actually the paper that I was referring to. So the answer is yes, but you need to add cues to the data structure. So you could also take semaphores, and through semaphores you could implement a monitor. And therefore you could implement basically a reentrant lock with a waiting condition. But the explanation why that might be possible is actually more complicated and not something that you are required to know for the exam. That's why if you want to know more, I provided like one extra paper, which should be here. Let me show you. So if you're going to Canvas, you're going to the modules, and then you are going to see G.R. Andrews, a method for solving synchronization problems. That is actually giving you the answer. How to use, for example, semaphores for implementing monitors. And that should be similar. Then the other thing, like the count latch or the barrier, are just, how do you say, adding more information or adding more specification to achieve a specific kind of synchronization. But basically, you could think as the monitors unlock to be the basic building block to also create the other ones. So definitely if you have like a counting latch, then you're also counting how many threads are being there, similarly to the barrier that I was describing before. Somehow the behavior is similar, but with which you could also implement the lock, but you could do that by enforcing that only one element at a time should pass. So you're creating a barrier for at most one element, so to speak. So you need to tweak the other implementation to actually achieve the same degree of complexity that you have for the lock. So then the answer, briefly speaking, is yes. Monitors give you more control, and given that you also have waiting conditions, are easier to handle. So if you're also having semaphores, then it's going to be very weird the way you need to wait for a condition. So you could also use monitors for waiting for a condition, which is going to be, this one. Where is it? So this is actually the thing that I was telling you. This actually, the slide 5 is how to implement semaphore with locks. And then you have example on how could you achieve producer and consumer implementation using a bounded buffer, but that is going to be more complicated. So you need to have 3 semaphores, one for the mutex, so for the mutual exclusion, the other one for checking whether something is empty, and the other one for checking whether something is full. So each waiting condition basically is implemented by another semaphore. And it's actually not straightforward how they operate. So you could do that definitely, everything with the semaphores, but it's going to be not straightforward. And it's going to be very easy that you commit errors if you are in a rush. Then if you're doing some careful implementation, that's for sure. You could always do everything with everything, but it's going to be more complicated. So the answer in some extent is yes. You could also do them. They are somehow equivalent. Does that answer the question? Or you still have? Okay, no worries. Any other question? So given that there are only 7 minutes left, as actually it doesn't make no sense to me to start discussing Dijkstra or Peterson's algorithm. So we're going to see that next week alongside with the semaphores. Let's have a nice weekend. one thing that I almost forgot, now if you want, you should also be able, after Wednesday lesson, to do exercise 2. And if you want, you could also do the most of exercise 1 and 3 for training for the open questions for the exam. So that's why I'm saying we already covered the majority of the material. So if you want, please feel free to do our exercises, and that was it. Yeah, questions? Sure.
So the topic ID, how many digits does the topic ID?
So you always are going to hit somehow machine limitations. So so the tests are not going to exceed the maximum number of integers. So the thing is, you shall never expect to use more than millions of, I'm never going to handle millions, okay? Because that is actually the maximum value that an integer might take. So in the worst case scenario, you're using basically big decimals, so, but we're not going to do that.
And what is the minimum?
So the minimum is 1. Either you have 0 elements, so you have not even the value 0 associated with that, or you have at least 1, so you're starting counting from 0.
Started from 0.
Yes, for example. No worries.